Here we have an alpha particle in a mass spectrometer setup. So the little positively charged helium nucleus or alpha particle is going to start down there. It's going to come up through the opening and wrap around something like this. And we're going to find out the magnetic field as well as the radius of the path in the setup. Now I know my alpha particle is coming in at 16,000 meters per second, and the electric field is 7,500 newtons per coulomb, and then we can also find out the other things from that. But first things first, I'm just going to find out a couple things with my alpha particle. Now, using the periodic table, I know that an alpha particle, of course, is helium-4 and using the atomic mass number and the atomic charge for the proton, all that kind of stuff, I can find out that the mass of my nucleus is approximately 6.68 times 10 to the negative 27 kilograms. And the charge is about 3.2 times 10 to the negative 19 coulombs. Now, I also am going to draw out my electric field first. Now, if I draw my electric field, I know the magnitude of it, but the electric field only belongs in the bottom part. Now, since the magnetic field is pushing it towards the right, I know that my electric field must be pushing it to the left. So I know that my little charge here is positively charged. So if there's a force towards the left, I know this would have to be the positive side, and that would be the negative side to try and get it to go towards the left. I know my FE has to go left. And positive charges go with the electric field, so my electric field must be going across something like this. And I can use that to also figure out my magnetic field. With my magnetic field, the magnetic force must be going towards the right in order to actually cancel out the electric force. Otherwise, the bottom part would not be a velocity selector where the two forces are equal. So using my right-hand rule, I know that my charge is going up. My force has to be to the right. And if I use that, I can see my magnetic field would be a series of dots, where the field will be coming out towards me. And of course, the field exists in both parts. I'm going to keep it the same everywhere. So it might look something like that. Now, to find the magnitude of my magnetic field, I can use the velocity selector expression. V is equal to E over B, because the two forces are the same. We've derived that before. And the magnetic field strength is just the electric field divided by the velocity. So I've got my electric field, 7,500. I've got my speed or velocity of 16,000. And I put those two together, and I can see that my magnetic field strength is approximately going to be 0.47 Teslas. And it is going into the page. Out towards me, out of the page. So now that I have that, I can now look for my radius. Now there's a couple ways you can find the radius. There's three main forces. We've got an electrical force, we've got a magnetic force, and since there's circular motion, we also have FC, and all three forces are equal, so you can use any combination that you want. Now, to keep this nice and simple, I can equate those two if I want. And if I equate those two, I would have the electric force is going to be equal to the centripetal force, which allows me then to solve for my radius of the path. So rearranging, radius would be mv squared over qe. And of course, you can also do something like this with FB, but I'm going to use FE just for the sake of using FE. So I've got my mass, I've got my velocity of 16,000, I've got my charge of 3.2 to the negative 19, as well as the electric field. And if I do that, I can calculate the radius of the pathway, and the radius of the pathway would be approximately 7.1 times 10 to the negative 4 meters. So that is the radius of the path over here as the alpha particle loops around.